Heat and temperature change. At the beginning of this unit, we introduced the idea of temperature, and we talked about heat as well. There is a relationship between the two, but it is that heat relates to the change in temperature, as we'll discuss in a moment. Let's consider the following. When you pour hot water into a cold cup, the water cools down and the cup warms up. Eventually, they'll have the same temperature. We call that thermal equilibrium, and this is something we'll discuss in more detail a little bit later. The reason for these temperature changes is that energy flows from the higher temperature object to the lower temperature object. This flow of energy is called heat, and we use the symbol Q to denote heat. Now, heat and temperature are different. Temperature is a quantitative measure of an object's hotness or coldness. Heat is the energy that moves from one object to another because of a temperature difference. What about the units of heat? Well, because heat is just another form of energy, we use the joule, the SI unit for energy. There are other common units of heat, and you'll hear these from time to time. One is the calorie, abbreviated lowercase CAL. This is the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius. 1 calorie is 4.186 joules. Another unit is the kcal, or kilocalorie, or calorie, but with a capital C. This is the one that you'll see whenever we're talking about calories in food. 1 kcal, 1,000 calories, is equal to 4,186 joules. Then finally, you may from time to time hear of the BTU, or British Thermal Unit. This is the quantity of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. 1 BTU is 252 calories, or 1,055 joules. Now, let's look at the relationship between heat and change in temperature. Well, consider a cup of water. Here we have one shown. It's at 10 degrees Celsius. If it takes an amount of heat Q to raise the temperature of the water by 10 degrees to 20 degrees Celsius, it will take twice that amount of heat to raise its temperature by 20 degrees to 30 degrees Celsius. So, the heat required is directly proportional to the change in temperature, or we have Q is proportional to the change in temperature. Now let's look at how mass has an effect on how much heat is required to raise the temperature of an object by a certain amount. Consider the cups below. Number 1 contains half the mass of cup number 2. If it takes an amount of heat Q to raise the temperature of cup number 1 by delta T, it will take twice that amount of heat to raise the temperature of cup number 2 by the same delta T. So we can say that heat required to get a certain temperature change is directly proportional to the mass of the object as well as the temperature change. So now we have Q is proportional to mass times change in temperature. We've seen how the change in temperature and the mass of a substance determines how much heat is required to change the temperature of that substance. But now, what if we compare different substances? So far we've talked about water. So let's consider the following. We have two objects. On the left, a mass m of water at 10 degrees Celsius. On the right, a piece of copper of the same mass at the same temperature. Now, experiment tells us that it takes less heat to raise the temperature of the copper than the water by the same amount. So, heat required depends on the nature of each substance as well. And that quantity that tells us about the effect of the substance on the heat required, we call the specific heat. And we use for that a symbol C. So what we've ended up with is the heat required to raise a mass of a given substance by delta T is given by this equation. Q equals mc delta T. Let's try to work out the units for specific heat. If we start with our equation, Q equals mc delta T, we can rearrange it for C, and we have Q over m delta T. Well, if we substitute the units for each of these variables, we get joules divided by kilograms times degrees Celsius. Joules per kilogram degrees Celsius. That's the unit for specific heat. Here's a table with some example specific heats. What's interesting about this table is that water has the maximum specific heat, and relative to the metals on the table, aluminum, copper, and gold, it has a much higher specific heat. So the meaning of this is it takes less heat to raise the temperature of a mass of a metal by delta T than it takes to raise the same mass of water by delta T. Another way of looking at this is if I heat a 1 kilogram piece of metal and a 1 kilogram amount of water with the same amount of heat, the water will have increased in temperature by less than that of the metal. That's why, given the same mass of a frying pan and a pot with water in it, heated for the same amount of time from the same initial temperature, if you have to stick your hand on one of them, your best bet is going to be the water in the pot.